Assalamualaikum warahmatullahi wabarakatuh and a very good day. Today we are going to cover on the example 9.51 in your textbook together. Okay, so you can do the exercise together with me throughout the video. Okay, so the question mentioned here that it is the standard heat of reaction is given. Okay, for the oxidation of ammonia. Okay, so this is given in the question. Okay, so also given to you is the chemical reaction for the oxidation process. So in the second statement, okay, they mention the flow rate. Okay, the flow rate of ammonia and also oxygen fact. So the inlet flow rate, and then the ammonia during the reaction is completely consumed. Means that no outlet of ammonia going out from the reactor. No ammonia going out from the reactor. Okay. So the product gas emerges at the temperature 300 degrees C. Okay. So determine the heat. Okay, that must be transferred to or from the reactor. So we don't know whether it's an exothermic or endothermic yet. Okay, so Q, heat is Q, assuming that the operation is approximately 1 atm. So we assume that this reaction, the pressure is equals to 1 atm, atmospheric pressure, okay, throughout the process. Okay, so now you need to translate the information into the next part, which is the flow chart. Okay. Okay, so as normal, we sketch our flow chart. Okay, so one block. Okay, so one inlet. Okay, and then one outlet. So normally in the reaction process, the inlet and outlet is only one. It's a normal one. Okay, so given to you is 100 mole of ammonia. Okay, and then 200 mole of oxygen. Okay. Temperature inlet is 25 degree T in 25 degree Celsius. Okay. Next one is the outlet. Okay, so we can start off with the product gases. Okay, so N1. Okay, molar flow rate N1. For mole of our first product is the nitrogen oxide. First, second. Okay, and then also water. Okay, mole H2O. Second. And then we can exclude ammonia because it's already mentioned, or you can include as well, no problem. Okay, so we can say that N3 mole NHD second is equals to 0. Okay, mole per second. No problem. Also, and then the final one is the flow rate of oxygen. Okay, so this one, once the material outlet is we mentioned, then the operating condition, so temperature out, okay, is at the 300 degree Celsius. So pressure is not mentioned here, however you can just put, so pressure is 1 atm. Okay. So once you solve that one, then we can move to the next part, which is the material balance calculation. So we can start with the extent of reaction, determination of extent of reaction. Extent equals to the, because we already know the outlet molar flow rate of ammonia, so we can choose ammonia as our calculation, substance for the calculation. And NH3 out minus VDN NH3 in. Okay, so it's a molar flow rate. So there's some column here. So it's a positive throughout the process, calculation. So and then the stoichiometric coefficient of ammonia. Okay. So for this one, we know 0 minus with the 100 inlet of ammonia divided by the stoichiometric coefficient is in the question. So ammonia is stoichiometric coefficient is equals to 4. Okay. So divide by 4. So you get your extent value equals to 25 mole per second. Once you settle with this one, then you can list out the extent equations for all substances. Okay. So for example, for the uh, NO, so we know that N1 is equals to the extent times the stoichiometric coefficient. So stoichiometric coefficient for NO is 4. So times the extent. So no inlet given throughout the for the NO. Let's go to the next slide. Okay. So we already know our extent value. So times with 20. You know the answer already. Second. So in that one, we move to the water H2O. H2O and 2. Okay, so inlet, no inlet for water. And then the stoichiometric value is 6. Okay, and then time with the extent. Okay, so 6 times with 20, 151 per second. Okay, so finally is the oxygen. So in 4. Okay, in our figure. So N4. So inlet for oxygen is 200 minus with the stoichiometric value 5 times the extent. Okay, so 200 minus 5 times 20. You will get 75 mole per second. Okay. So once we settle the material balance, we can move to the reference state and the inlet outlet enthalpy table. So I already take out the inlet outlet enthalpy table. So for reference state, okay, reference state. So you need to determine which method you are using. So if you notice in the question, they already give you the standard enthalpy of reaction. So because the question already give you the standard of enthalpy of reaction, so it is easier for us to use heat of reaction method for the calculation. Okay, so for the heat of reaction method, the reference state must be in a substances. Okay, substance. Okay, and then 25 degree and 180 M. So you can refer to the energy valence procedure in page 450 or 274, 374 in your books. Sorry. Okay, so for the heat of reactions, so it's in terms of substances. So inlet and outlet. So our substance in the reaction. So you just state whatever substance in your chemical reaction. Okay, so for our case, our substance is ammonia, which is in a gas phase. Okay, and then oxygen, also in a gas phase. Okay, and nitrogen oxide, gas phase, and then water in a vapor form. Okay, so at temperature 25 degrees C and 1 atm pressure. Okay, so this is the reference state. So we have marks in the test of an exam only. So ensure that you write down your reference state. Okay. So completing the inlet and outlet enthalpy table. Okay. So for this one, I just change a bit the color. So just put based on our reference the substances. So we have ammonia, okay, and then oxygen, NO, and water. Okay, so this one is based on our calculation just now, the molar flow rate in and molar flow rate out. So given in the question for ammonia is 100 and for the oxygen is 200. Okay, so no inlet for outside and water. So the enthalpy for inlet also 0. Okay, so for the here enthalpy in, ammonia and oxygen inlet is 25 degrees Celsius temperature in. Okay, so temperature in is equals to 25. Okay, because the temperature in is equals to our reference state. Okay, because it's equals to our reference state, then the enthalpy is equivalent to 0. Okay, okay. So now we move to the molar flow rate out. So ammonia outlet is 0, not available. Okay, because it's completely reacted. So for oxygen, we calculated just now 75, and then O is 100, and then water is 150. Okay. So enthalpy out, temperature out from the reactor just now is 300 degree, right? Okay. So it's different with our reference state. So there's a value that you need to do the calculation. So before we know the values, we just state the enthalpy as H1, H2, and H3. Okay. So once we complete our inlet and outlet enthalpy table, okay, we can move to the calculation part, which is the unknown specific enthalpy. So our unknown just now is H1 till H3. So we do not know what is the enthalpy value. Okay. So for H1, the substance is oxygen. Okay, it is in a gas state, and then the temperature is 300 degrees C. So this is our reference state, right? So if you refer to table B8, okay, so table B8, okay, so there's a condition for gas, okay. So oxygen, okay, list of gases, okay, oxygen, even water, hydrogen, okay, carbon dioxide, carbon monoxide, the normal gases found in the processes. So you can see the values, okay, enthalpy there. Okay, so it's equivalent to enthalpy at 300 degrees. So you take the temperature 300 degree is equals to 8.47 kilojoule per mole. You just can take it directly, the values. Okay, don't have to do any other calculation. Okay, okay. So this one, and then next substance is the side. Okay, so also in a gas phase, temperature 300 degrees C. Okay, so this substance is not in table B8. So because you don't have it in a table B8, you need to refer table B2. Okay, so table B2, you need to find the nitrogen oxide. Okay, so H2 integration from reference state 25 to our desired temperature 300 degree Cp dt. Okay, so if you refer to the table A2, B2, then you know that your A is equals to 29.5 times with the 10 to the power of negative 3. Make sure you translate the data correctly. Okay, 0.8188.5 and C is equals to negative 2, sorry, 0.2925 times 10 to the power of 8, and then D equals to 0.3652 times 10 to the power of 3. Okay, so you include all the values into the CP equation. Okay, it's in your top of the table for the CP data. Okay, A plus B, A plus BT plus C T power of 2 plus D T power of 3. So you take the first equation, right? And then do the integration. Or it's easier for you to do the calculator, just directly use your calculator to do the calculation. Then you get the enthalpy for NO is 8.453 kilojoule per mole. Okay. Fine. Now we move to the last substance, which is water, H2O, which is in a vapor phase. Okay, and then temperature also 300 degrees C. Okay, so this one for water also you can refer to table V8, so you don't have to do the integration. Okay, so we check the at the temperature 300 degree. For water in a vapor or gas form only. Okay, so you get the data 9.57 kilojoule per mole. Okay. Once you have all the information on the unknown enthalpy, then we can do the calculation for the enthalpy change. Okay, which is what the question requested. Okay, so we know that the change of enthalpy. So I just straightforwardly just do write the equation x10 times the HR standard, okay, times the summation of N and H out, okay, minus the summation of N and H in. Okay, okay, so x10 you already calculate just now in the material balance calculation, 25 mole per second. Okay, and then the uh, standard enthalpy reaction is in the question given near to the reaction, negative 904.7 kilojoule per mole. Okay, so you can put the molar flow rate and the enthalpy outlet, just directly take it from the enthalpy table in the outlet enthalpy table. Okay, so the first substance 25 8147 plus with the 100 oxygen and O 3 and also water 150 9.7 level. Okay, and then the inlet is 100 times with 0 minus extra 200 times with 0. Okay, so this one, sorry, the unit for each of this one is mole per second. Then this one is kilojoule per mole. Okay, for all of them. Okay, so basically you remove the mole unit from the calculation, so you can get the final answer. Okay, so this one as well. Okay, you can get the final answer negative 19,700 kilojoule per second. So we know that joule per second equals to watt. So you can simplify negative 19,700 kilowatt. Okay. Okay. So the very last step of this part is the determination of the question, what the question requested, right? Okay, so we always start with the general equation of energy balance. So if you notice, it's a open system, right? Open system. So we know that Q plus with the change of EK plus with the change of EP equals to, oh sorry, delta H, okay, plus delta EK plus delta EP equals to Q minus W. Okay, so the question doesn't mention anything about movement, and then potential, so height also is not involved. So we know our Q is equal to data H. So equivalent to directly take the information here, code it, 19,700 kilowatt. Okay, so equals to negative 19.7 megawatt. Okay, so that will be your final answer. Okay, so that's all for example 9.51. Thank you very much.